Now, this is the pedestal grinder, and the pedestal grinder is a tool that we use in the shop to grind materials that we would like to form a shape into. We have some rules about the grinders in our shop that may be different than you're used to as far as a home grinder, but there are reasons behind those rules. Some of the things I want to tell you about to start off with that are safety related: this guard right here, this ledge that you can rest your tool on, is called a tool rest. There's a gap in front of the wheel so that the wheel can spin. That gap can be no larger than 1/8 of an inch. It is an OSHA regulation, so we have to make sure that we do not let that gap get too big. One of the reasons for that is so that nothing can get sucked down in there, preferably you. We don't want you to get hurt on here. One of the other things that we want to make sure of is just a repeat of some of the earlier statements that's safety related. We never wear gloves in this shop. If a corner of your glove got stuck down in there while this grinder is running, it'll pull you right down into it. It's going to create a pretty nasty injury. We're going to use the grinder to grind our tool bits for the lathe, and you'll see how those tools are mounted in another section. One of the things that we want to make sure of is that we only grind ferrous materials in our shop. That is a rule. The only materials that we allow people to grind in our shop are ferrous materials. Basically, if you can stick a magnet on it and the magnet sticks to it, you're good to grind it. If not, don't grind it. That does not mean that there are not materials that are non-ferrous that are safe to grind. Tungsten. If there are any welders out there, you'll know that you can grind a TIG electrode. There's nothing wrong with it. It's not going to hurt anything. And tungsten, well, it's made of tungsten. It doesn't have any iron in it. So there are materials out there that are non-ferrous that are safe to grind. However, all of the unsafe materials are non-ferrous. So we just draw a line in the sand in our shop. Only ferrous materials are allowed on the grinder. Things that we want to pay special attention to that people bring over here, and we will kick you out of the shop for grinding them. Wood. Wood is a problem because the short little fibers will get wedged up inside of the grinding wheel, and it will do what's called loading the wheel up. It basically means that the whole front of the wheel that does the cutting gets packed full of stuff, and you have to grind away at the front of the wheel, and it is mainly a cost and annoyance issue. Same with plastics. Plastics will do the same thing. They'll get in there and they'll pack up the front of the wheel, and you have to grind all that material off of the wheel, which is just a waste. We don't want to do any hazardous materials, things like lead. You don't want to breathe lead dust, things like that. Carbon fiber. We don't want to grind on carbon fiber. Breathing those particles in can be harmful. Fiberglass, that's another one we don't want to do. One that I'd like to pay some special attention to is aluminum. Aluminum is one that can be very, very dangerous to grind. Different circumstances can arise that could cause the wheel to explode if you grind aluminum. This wheel is spinning at about 3,700 RPM, and this is a double-ended grinder, and these are 7-inch diameter wheels, so they're much bigger and much faster than a grinder that you would have at your home. If you grind aluminum, aluminum will load up the front of the wheel, and as you grind on it, it will create a fair amount of heat, and that heat will cause the aluminum to expand, and that aluminum that worked its way down into the porous nature of the grinding wheel can expand, and it could potentially cause the grinding wheel to rupture, and if it does that while it's spinning at full speed, that's not good. So we want to avoid that scenario. So definitely no aluminum grinding. So what are we going to grind? Well, in this lab, I'm going to show you how to create your lathe tool. Your lathe tool will be in your toolbox. It'll probably come packaged something like this. Now, I've pre-opened this one. They can be a little tricky unless you have a knife to get them open. This bit right here is called a Lathe Tool Bit or a Lathe Tool Blank, and it is made out of high-speed steel. High-speed steel is a hardened tool steel that is pretty tough. Right? It has some alloying agents in it that make it very tough. They make it pretty fracture resistant, even though it's very hard. One of the things that we know is that the harder the materials are, the more brittle they get. So we want to try and find a material that is hard but not brittle. High-speed steel does that for us. Now this blank, if you look at it, has a little bit of an undercut on one edge. If you notice, it's got an angle like that. Ultimately, it doesn't really matter where we start, but once we do start, we are going to maintain the top of the tool throughout the entire process. So what I find it helpful to do is to actually mark the top of my tool with a Sharpie or something so that we can identify the tool as such. So as you can see, I have marked the top of my tool with a Sharpie, and that is from this point forward going to remain the top of my tool. When we go to power on the grinder, this switch right here turns power on to the grinder. It also sends the signal to the dust collector, but we need to make sure that the dust collector is powered up. Sometimes people will turn the power switch on and off, trying to be helpful, but they end up causing a little bit of a confusion. So if we turn this switch on, we should see power go to the dust collector. And as you can see, the dust collector light comes on, and the wheels are spinning. One thing to take note of is how long this wheel will spin. This wheel will spin for minutes. So we need to be observant of that. You need to make sure that you are cautious around the grinders. Anytime you walk up to a grinder, I think that it's a good idea to assume that it is always running. That doesn't mean leave it running. That means if you're going to work around the grinder, you need to always assume it's going to be running until you are 100% sure that it is not, because it can look very deceiving when you walk up to it. The first grind that we are going to do on our lathe tool, we are going to have the top of our tool facing up, and we are going to kick the back end of our tool over to the right about 20 degrees. And we are going to grind the entire front of that tool until the tool is completely ground from one side to the other, top to bottom. Now the first thing that I'm going to show you prior to doing that grind is what happens as we're grinding and we start to build up a lot of heat. I'm going to intentionally push this tool into the grinding wheel and let it sit there and build up some heat so that you can see the effects. Now that tub of water that I just quenched the part in allows me to cool the part down, and we're going to use that water while we're operating on these tools. If you'll notice this color band here, as you start to generate a lot of heat, the material will actually change color. And the darker the colors get, in general, that means the hotter the tool is getting. We really want to avoid those dark colors. Now, as anything, grinding wheels can actually get dull. When they lose those sharp, crisp edges on the outside, we need to dress the wheel. To dress the wheel, we use a wheel dresser. It's a tool that looks like this. These wheels are diamond impregnated, and they spin around at random and break up the outside edge of the grinding wheel. We want to do that in a very smooth and uniform fashion, and it makes a lot of dust and noise, and you will likely feel little particles bouncing off of your skin. It's not going to hurt, but you will feel it. It would be like if you were at the beach on a really windy day. You'll feel little particles of sand hit you. That's about what it feels like. It is loud though. We're looking to create a uniform surface across the front face. I'm going to finish grinding that first grind. There again, the top of my tool is facing up. I'll kick it over at about 20 degrees, and I'm going to work it back and forth and grind that entire face until it is flush all the way across. As the tool starts to heat up, quench it in the water. As you can see, we've got a nice clean edge right there, and if you look at the front from top to bottom, it is completely ground. That's our first grind. Our second grind, we're going to have the top facing up. This was our original primary grind. We're going to swing the tool around to the left. The top is up, the tail of the tool is facing to the left. And we're going to go straight in about half the width of the grinding wheel. We're going to basically push straight in, making sure the entire time that our tool never comes off of this tool rest. It's very important that your tool not get moved around during these grinding operations. You can move it back and forth just a small amount, but you really don't want to do a lot of grinding or moving around while you're grinding. As you can see, it's bringing that grind up from the bottom toward the top, and I'm maintaining a parallel grind. That's very important. We want to hold this edge parallel to the front of that grinding wheel. We want to grind this until that entire surface is completely ground, top to bottom. See, the entire surface is ground top to bottom. There are no remnants of an unground surface. You have to look very carefully right at that top edge to make sure that there are no remnants of an unground surface on there. So that's the second grind. the third and final grind, we're going to take the top of our tool facing up, swing the leg, the back side of the tool over to the right this time, and now we're going to rotate the tool 90 degrees to where the top is facing the grinding wheel, just like that. And we're going to essentially create the exact same grind that we just did. The difference being, I want to angle my tool with the tail a little bit toward the back of the grinder. Now this is very exaggerated so that you can see the direction that I want you to have the angle in. We only want that angle to be a half a degree, 1 degree. So almost parallel, but just a tiny bit in that direction. You can see, even with that very small amount of angle, that you get a very different grind pattern. You see the grind is at an angle there. That's too much. I need to back off of that angle a little bit. May be kind of difficult for the camera to catch, but you can see that that's a much shallower angle. That's what I'm looking for, something like that. Go. That's how to grind your lathe tool. When we are working in a shop environment, we have to remember that we have to choose the units we're working in. And in our shop, we are an English shop because all of the machines are based in inches. So we're going to discuss English units in depth. And what I need for you guys to understand is that we have to think about numbers in a very specific way so that as you work in the shop, you don't get confused. And when we take measurements, you don't get confused. So we really need to think about numbers in a little bit of a different manner than you're probably used to. Whenever you look at this number, 0.1 inches. Many people, if I asked them, how would you say that number? You would say it's 1/10 of an inch. I want you guys to get away from that thought process, and I'm going to try and explain why it's important to think about things in a different manner when you're working in the machine shop. In the shop environment, our base unit is 0.001 inches, or 1/1000th of an inch. There are many different names that this can go by. You can call it a thousandth. You'll hear people refer to it as a thou. In the plastics industry, the thin film plastics industry, you'll hear it referred to as a mil. You may see that on plastic bags, plastic sheeting, rubber gloves, or latex style gloves. That's where you would likely see that as an inch. But that is our base unit in the machine shop. Pretty much all of the numbers that we're going to refer to ever are going to be referred to with reference to that number. This may seem trivial at first and you'll just brush it off, but this is a cornerstone of understanding how to cut materials, how to take measurements and things like that. So I urge you for at least the beginning portion, whenever you start to work in the shop, to reference everything to 3 decimal places, even if you don't need it for the time being, just to get your head wrapped around operating in those terms. What do I mean by that? If you needed something cut to 0.01 inches, that is 10 thousandths of an inch, because it's 10 of these. 0.1, like we said earlier, to 3 decimal places, that's 100 thousandths, because it's 100 of our basic unit. So this is not a tenth, this is 100 thousandths. Now, why am I making a big deal about that? Because in a machine shop, a tenth is a tenth of this base unit, or 1/10 of 1,000th of an inch, which is 0.0001. And there is a massive difference in the sense of scale between those two numbers. For a point of reference, how big is 1,000th of an inch? To start off with, it's very small. We need to figure out some way for you guys to understand how big or how small it really is. The average human hair is somewhere between 4 to 6 thousandths of an inch. 20-pound copy paper that comes out of the printer is about 4 thousandths of an inch, pretty repeatable. So, what does that mean? Probably not a whole lot to a lot of people, but how big is 1,000th of an inch? If you take a sheet of notebook paper or 20-pound copy paper and you slice it into 4 even thicknesses, that's 1,000th of an inch. Now you're starting to see how tiny that number really is. Or if you were to take a human hair and slice it into 4 even pieces or 5 even pieces, that's 1,000th of an inch. So when we start talking about a tenth of 1,000th, we're talking about taking a sheet of notebook paper or a sheet of 20-pound copy paper and slicing it into 40 equal sections thick. Or a human hair and slicing it into 40 different slices. That's pretty tiny. I want you guys to think about this. If you have questions, always ask. And next we're going to talk about metric units. So in a metric shop, your base unit that you will see is 0.001 millimeters, or 1,000th of a millimeter. This is commonly referred to as a micron in industry. You will hear in academia this referred to as a micrometer, but in industry the common terminology is a micron. One of the reasons we don't use the term micrometer in the machine shop is partially because there's a tool called a micrometer, which is spelled the same way, and it just gets a little confusing. So you will hear the term micron constantly used in metric shops, and that 1 micron is 0.001 millimeters. One of the other terms that I would like to tell you about is a nanometer, which is 0.00001 millimeters, or 1/millionth of a millimeter, or 1/billionth of a meter. The reason I even bother talking about a nanometer is because of the prevalence of nanoscale things in the current environment. Nanoparticles, nanotubes, nanobots, nanorobots, nanomachining, lots of different things. This is an extreme scale. A nanometer is infinitely small. It is almost unfathomable, the size and the scale of a nanometer. I urge you to try and get a sense of how big that is, and that is something that is very difficult for me to explain. 1 micron, if you look at high efficiency filters, air filters, they will be filtering dust particles and smoke particles that are on that level of size. So if you're talking about something that can, a particle that is on the order of 1 micron, it takes a HEPA style filter to actually filter particles that small out of the air. So you're talking about very, very, very small particles. If we refer it back to something that I talked about earlier, a sheet of 20-pound copy paper is about 4/1000ths of an inch thick. 4/1000ths is the equivalent to approximately 100 microns. So if you divide that sheet of 20-pound copy paper into 100 equal sheets, that's 1 micron. Or if you were to divide the average human hair into 100 equal slices, that is 1 micron thick. So it is a very, very small thing. So just to put it into perspective, 4/1000ths of an inch is a sheet of 20-pound copy paper. 100 microns is the same measurement. So you can tell a micron is much, much smaller. So what we are going to discuss right now is a dial caliper and how to read a dial caliper. One of the reasons that I like using a dial caliper in the machine shop, for starters, it doesn't take a battery. And over time, they are very repeatable over a long term as long as you take good care of them. Don't drop your dial calipers. Don't be real rough with them. Store them in the case. Keep them clean. Don't let chips and dust and dirt get in them. And you can use them for decades. Drop them a couple of times. You can use them for minutes. So it really depends on the care that you give. What I've drawn on the board here is a schematic of a dial caliper, and as you can see in the picture that I've shown earlier, that's what the face of the dial caliper is. I'm going to go through the method that I would suggest you use to actually read a dial caliper every single time. So as you open the jaws of the dial caliper, you will notice that the needle on the dial starts to rotate. As it rotates, it's going to spin around and it will give you a reading, and you will always read this dial from 00 to 99. So it's going to start off at 0, and it's going to work its way around, and you'll go from 00 to 99, and then you'll restart at 00 and 99. When you're taking measurements, I want you to start with the first thing you write down being the reading from the dial. We're always going to take a 3-digit measurement when using a dial caliper. We're going to end up with something in this form, this X dot Y ZZ form. The ZZ is the 2 digits from 00 to 99 that you get off of the dial caliper. The next number that we will come to is the Y value. And the Y value comes from the 100,000ths place. Right? It's right there after the decimal, so it's the 100,000ths place, and it's going to come off of the scale at the bottom instead of the dial. If you look at the bottom scale, you'll see that there's 1, 2, 3, 4, 5, 6, 7, 8, 9, and then a new inch, and then 1, 2, 3, 4, 5, 6, 7, 8, 9. You'll see that there is a slide that moves to the right. As you open it, this thing's going to be spinning around, and it's going to go from 0, 0 to 99, and then as soon as it gets back to 0, 0 again, you'll have uncovered the 100,000s. So it's going to start at 0, 0, open up, and it'll get back to 0, 0 at 100,000s. That would be a 1 and then a 0, 0 again. So as you uncover, you're going to write down the 100,000s place. And the easiest one to get and forget sometimes is the inches, because it's either 1 inch, 2 inch, 3 inch, 4 inch, so it'd be in here, in here, in here. That's the X value. Please be very careful and conscientious with the Y value. It's the one that trips people up a lot of times, because you have to be conscious of where you are at, where you are counting up to. If you open it up to say 295 thousandths or 397 thousandths, something that is very close to the next value, it's very easy to just glance at your calipers and pick the next highest number, because you will physically be able to see that next highest number. It's because it's almost there. And if you refer back to when we said how big is 1,000th of an inch, or how big is 3,000ths of an inch, if we're at 397, we are only 3,000ths away from 400 thousandths. And if you remember, that's less than a sheet of printer paper thickness away from that value, which means that we are right on top. So you're going to be able to see that value in the Y. So please be careful. This is where some practice with measuring things that are known values really comes into play. There's lots of stuff that you can measure, that you know the answer to. I would suggest opening your calipers to known values that you can compare to a scale. So you can say 1/4 of an inch. We know that that's 250 thousandths. 250 thousandths is 1/4 of an inch. I can open up to what I believe is 250 thousandths and then compare that to a scale and say, am I right or wrong? You can open up things like bigger values that are closer to these numbers right up near the edge. And you can say, okay, I know that 15/16ths is this value, or whatever values you choose, and you can compare them to a scale and say, okay, am I right on the money? Am I way off? What's going on? Because what you'll notice is that if you are off, you will be off by a full 100 thousandths, which is easily noticeable if you're comparing that to a scale. So, there again, any questions that you may have, please come and ask one of us. I really, really want to urge you, when you first start writing, or when you first start measuring things with dial calipers, to actually physically write the number down and consciously write it in 3 decimal places, and start from the dial, writing the last 2 of the 3 decimal places down, work your way back to the 100 thousandths place, and then finally writing down your inch value. That will help you to solve many of the problems that you will face. I want to talk to you about cutting speeds of materials and where these units kind of come from a little bit. When we start talking about physically cutting a material, there is a limit to which we can drag the tool through the material. It's a physical barrier, it's a physical limit. And it depends on a lot of things. It depends on what your tool is made out of, what the material is that you're cutting. So there's lots of different things. These numbers over here are given for high-speed steel tooling. All right, and these are just some example numbers. They are not definitive, but they are a good reference point to start from. You will see some deviation from these numbers, but these are just good general starting points to go from. For using a high-speed steel tool, if we're cutting through a stainless steel, we would want to use 50 surface feet per minute. And that is a bit of an awkward measurement, but in English units, that is the standard unit that we go by. If we're cutting through a type of annealed tool steel, such as drill block, there again, 50 surface feet would be good. If we're cutting through mild steel, which would be one of the components, well, many of the components for the air motor or many different items, we would use something around 100 surface feet. Brass goes up to 200, aluminum is somewhere around 300, and if we go into plastics and really soft materials like that, it may go upwards of 500 surface feet. And basically all that is that if you were to cut one tooth in a straight line, that's how far it would move in feet over a 1 minute time span. So you can see something made out of plastic, you can literally cut it 10 times as fast as something as a much tougher material such as a stainless steel or a tool steel. Now, we use these numbers to help us calculate RPM, and that could be for a drilling operation, that could be for a lathe turning operation. So it really doesn't matter if we're using a drill bit or an end mill or if we're turning the part in a lathe. All of these calculate the same way. What we have to do is look at the formula for RPM. And the formula, the longhand formula for RPM is 12 times the cutting speed that we found over here divided by pi times the diameter. Where does that come from? It's the surface speed converted into inches per minute, that's why we've got the 12 there, divided by the circumference, because that turns that into the linear amount of inches around the surface we're cutting. If we assume that 12 over pi is 4, approximately, we can convert this into a shorthand version of 4 times the cutting speed divided by the diameter. This is a handy formula that you should commit to memory. You will use this formula all the time. You will use it constantly in the machine shop because we need to calculate how fast our tool or our part is moving. We need to remember a couple of things. The diameter is always in inches if using this formula. And the diameter is the largest diameter where cutting takes place during that operation. If we're turning, it's the largest diameter that we're turning. If we're drilling, it's the diameter of the drill. If we're using an end mill, it's the diameter of the end mill bit. It's whatever the largest diameter that cutting will take place during that operation. There are two types of oils that you are likely to need to know the difference of when you're working in the shop. You're going to use these two oils all the time. We have a lubrication oil and we have a cutting oil. Lubrication oils are exactly what they sound like. They are good for lubrication. Cutting oils are something that you may not be familiar with. They assist you when you are machining metals to achieve a better surface finish and keep the cut cooled down. And there are different chemical compositions between the two. Lubrication oils are not good as cutting oils, and cutting oils are not good as lubrication oils. Cutting oils are easily identifiable in a container with a brush in our shop. We have these little spill-proof containers. You can see that there's an application brush in there. Lubrication oils, on the other hand, are easily identifiable in different types of application containers. This has a little pump on it. You pump it and it squirts out. We will go through how to lubricate the machines in a few moments, but I wanted to point out the difference between lubrication oil, and a cutting oil. Another point that I would like to cover right now is a safety concern with air lines. In our shop, we use compressed air lines. A couple of things that you want to know about compressed air. You never want to blow off chips from yourself. You're not going to use an airline like you may have seen people do in the past. You don't ever blow air across yourself. You don't blow air across your skin. All we ever use the airlines for are short bursts to clean out chips that have built up down inside of a part, or to clean off an area, and you will always see me use an airline in short bursts, just like that. You want to make sure that you never blow metal chips towards anyone, like especially in the face. You want to be observant as to where those chips are going to get blown. If you are standing over a pocket and you blow down in there with the compressed air, be aware that those chips are going to come flying out in your face. You want to be very cautious about that, which is why you won't see me hosing an area down with an airline. I think that that is bad practice. So please be sure that you make sure that you're aware of where you're pointing the airline, where the likelihood of the chips and debris are going to get blown when you do use an airline, and never use an airline to clean yourself or your clothing or anybody else off. Another point that needs to be made when using the airline, one of the things that we do in this shop is we maintain a clean shop. You are responsible for any mess that you make. And if you blow chips all the way across the shop, you are required to clean that area. So if you blow chips from one side of the shop to the other, you are required to clean that area, which includes as far as the chips go. So please be conscious and conservative when using the airlines. We have several methods for cleaning things up. A lot of times I will use a chip brush, which is like a paint brush. It's going to look like this right here, and you just brush the chips down, and it is very controlled. It does a good job, and you don't have to worry about the chips flying up into your face or someone else's face, and it's a much safer option. One of the things that we need to keep in mind whenever we are working on a lathe especially is that we need to be very vigilant about making sure that nothing that we have on our person can get caught in the machine. This is paramount whenever you are operating a lathe. You want to make sure that you have no rings, watches, wristbands, bracelets, anything like that that can get caught in the machine. We want to make sure that you don't have anything hanging down from your neck, such as necklaces or ties from a hoodie or anything like that that can get caught in the machine. It may seem like it would be pretty unlikely to get caught in a machine, but even in the unlikely event, we want to try and prevent that. Whenever we go to operate the equipment, prior to using it, we want to make sure that we lubricate the machine prior to each use. For that, we're going to use a lubrication oil. If you look on the machine, you will see many different lubrication points, and they look like these small brass ferrules with ball bearings in them. You take your lube oil, you press it in, and you go through all of the different lubrication points. And we're going to go through the entire machine and lube all of these points all over the entire machine. It takes a couple of minutes, but this will greatly extend the life of the machine. When you are in the lab, you will be assigned a machine that is your machine to use during your lab period. This box houses the keys to all of the machines in the lab. Each one of the keys in the lab has a number, and that number corresponds to the machine in the lab that you have been assigned to. If you look, all of the keys are separated by mill keys on the top row and lathe keys on the bottom row. We're going to start with the lathe in this set of instructions. So I'm going to get my lathe key. This is the instructor key. You do not use any of the keys that are on the inside of this door right here. Please make sure of a few things whenever you check keys out, that you take the key that is your key, you go to the machine that is your machine that key responds to. You want to make sure that you don't ever put these keys in your pocket, and the reason for that is we don't want these keys to leave the lab. You definitely don't want to lock these keys up in your toolbox and carry it out either, because the likelihood is that you won't recognize that you've carried the keys accidentally out of the lab. So the important thing is that these keys never leave the lab. We also want to make sure that you return the keys to their corresponding slot in the key box. That way it's easy for us to keep up with the keys that we need, and that we always have ready access, and they're orderly, and whenever somebody goes to check out their key, it's in the correct spot. Each spot is labeled inside of the key box. When you walk up to your machine, you're going to see that it's locked, and the keys that we talked about earlier are going to be used to unlock access to the machine. And you would need to turn the power to the machine on by turning the interlock. The tumbler key, the round tumbler key, is used to unlock your toolbox. When you're finished using your toolbox at the end of the day, make sure that you lock your toolbox back and that you put the lock back on the interlock to the machine. Whenever you turn the power on the interlock of the machine, you'll see that you get a power notification light on the front of the machine. This portion of the machine is called the headstock of the machine. One of the things that you will need to do most of the time is release this emergency stop by giving a slight twisting motion, and you will see that the lock releases. The headstock of the machine is what houses the spindle. The spindle is a rotating part that runs through the headstock, is mounted on bearings, and is what the front of the spindle comes out and is mounted onto a chuck. The chuck is mounted onto the front of the spindle. This front piece of the spindle is called the spindle nose. It is directly behind the chuck. The chuck stops at this edge and the spindle nose stops right there. The chuck mounts onto the spindle. This type of chuck is called a 3-jaw chuck. This is a 3-jaw simultaneous chuck. It is called a simultaneous chuck because all 3 jaws move at the same time whenever the wrench is inserted and turned. The wrench should never be left in the chuck at any given point in time. You should never take your hand off of the wrench until you set the wrench down. This is a major safety concern. These rails that run the length of the machine are called the ways. W-A-Y-S, ways. The ways are what allow this portion to run back and forth along the axis of rotation. This portion is called the carriage. The carriage moves back and forth in the Z direction on a lathe. On top of the carriage is mounted a cross slide. The cross slide moves in the X direction on a lathe. On top of the cross slide is a compound slide. The compound slide is able to be rotated to any angle. For the purposes of our labs, we mount the compound slide at 0 degrees to the axis of rotation. This gives us a higher level of dimensional control. On top of the compound slide is a tool post. This is called a quick change tool post. It allows us to mount a tool holder. This handle, when rotated around, allows us to lock the tool holder in. If you look, when this is rotated, you can see the wedge mechanism that locks the tool holder in to the tool post. The lathe tool that we created mounts into the tool holder. As we go toward the back of the machine, we have the tailstock. The tailstock allows us to hold tools such as drill bits and centers on the backside of the lathe. This handle releases the tailstock and allows it to be slid forward and backwards, and it locks it in so that it can't be locked or can't be slid. If you turn the handle on the tailstock backwards, you can remove the tooling from the quill that goes in and out of the tailstock. This type of taper is called a Morse taper, M-O-R-S-E, and it is a friction fit in the tailstock. In order to put the Morse taper in and successfully lock it into the tailstock needs to be extended. We will slide this in and give it a bump. When you do that, it will lock in with a friction fit. In order to remove it, there again, you will back the tailstock all the way down, and you'll see that it is being pushed out of the tailstock. As a recap of the parts, we have the headstock. Inside of the headstock is the spindle. The spindle rotates on bearings and is driven by the motor. We have the spindle nose. The chuck mounts onto the spindle nose. We have the ways that run back and forth. The carriage runs back and forth on the ways. The cross slide is mounted onto the top of the carriage. The compound slide is mounted on top of the cross slide. The tool post is mounted on top of the compound. The tool holder is mounted on the tool post, and then our tool sits inside of the tool holder. When mounting the tool into the tool holder, we need to make sure that the top of our tool faces up. We will slide the tool into the tool holder, and we need to make sure that we tighten at least 2 of these set screws to prevent the tool from rotating. And we want to make sure that the set screws are seated adequately. Make sure that you tighten the set screws so that this tool will not get pushed around. When we come up to the machine and we're ready to machine, we need to select the RPM that we want to use. And on these particular lathes, these 2 levers combined with this chart allow us to select the RPM that we want to use. We simply select the color and the letter, and we make that combination match in this chart, and we select the RPM that we want to use. The likelihood is high that you will need to rotate the chuck at the same time while you move the lever in order for it to actually engage the gears, because we are turning the spindle and getting the gears to mesh. You have to work the lever back and forth sometimes just a little bit. Now we're ready to mount a part to cut in the chuck. So we're going to take the chuck key and the part that we're going to demo. We will put the chuck key into the chuck, open the jaws large enough to accept the part, and we're going to tighten it very securely so that the part can't fly out of the chuck. Now, we have a couple of ways that we can spin the spindle. This green button on the front is called a jog switch, and what it does is it allows us to get power to the spindle while we hold that button in. So if I push the button, you see that the spindle runs, but as soon as I let that button go, the spindle is going to coast back to a stop. And that's simply handy at times for us to make sure that the spindle is in gear, allow us to see if something is running true. There's a lot of reasons that it's handy to have a jog switch. But whenever we're operating the lathe, we need the lathe spindle to continually run. And for that, we will use this switch right here. This switch on this lathe, if we move it down, will spin the chuck clockwise. If we lift this, it will spin the chuck counterclockwise. And the middle is the neutral position. If you need to stop the spindle from turning, you can simply lift up on the handle and let the spindle coast to a stop. If there is an emergency and the spindle is running, you have a couple of options. The first option is to hit the E-stop. This E-stop, as you can see, allows the spindle to coast to a stop. Prior to clearing the E-stop, I would suggest putting the handle back in the neutral location. Clear the E-stop, and now we are able to start the spindle again. There is another option, which is the emergency brake foot brake. It is a physical mechanical brake on the spindle. It will cause the spindle to stop very rapidly. I normally tell my students to reserve that for an actual emergency, but if you need to use it, use it. Never question whether or not you should use an emergency stop. If that crosses your mind, use it. If you have any question or you think anything is going wrong, never hesitate to use the emergency stop. To clear the foot switch, we simply have to raise the lever back into the neutral position, and it will start back up again once we clear it. I have mounted my tool into the tool post, and I'm going to turn the spindle on clockwise. Clockwise is defined as the top of the spindle coming towards you. That definition generates from being on the outside of the machine on the motor end, which is where the headstock is. So the outside of the machine on the motor end, looking down the spindle clockwise. If you're staring at it from this side, it's going to spin what you might perceive as counterclockwise, but that is not the way that the system is defined. Clockwise on any machine tool is defined as outside of the machine, on the motor end, clockwise. That is also referred to as the normal rotation of the spindle. So I'm going to turn the spindle on. I have locked everything into place. And the tool that we created, I want you to see how it is used. Is a turning move. I have chosen a material that is very forgiving and easy to machine, plastic, so that you can physically see the material that is being removed. A facing move moves the tool in this direction. Facing allows you to remove material off of the end of a part. Turning allows us to reduce the diameter of a part. When using a file on a lathe, you need to make sure of several things. First and foremost, the file has to have a handle on it. One of the wooden handles can protect you from serious injury on the file, or on the lathe when using a file on a lathe. You always want to hold the file handle in your left hand and hold the end of the file in your right hand. That way you're able to support the back of the file on the front and the back side of the part, and you never reach around or over the machine spindle. If you were to hold it opposite, you would be reaching over the spindle or the chuck, and that is a dangerous scenario that you do not want to do. So always hold the handle of the file in your left hand, the end of the file in your right hand, and you either push down or push across, or you can rotate around to achieve different end effects with the file to break the edge. I'm going to turn it on. Again, we want the spindle to turn by convention clockwise. That's all it takes to break the edge over and deburr the edge. Wait until the spindle stops and you can see the chips that were created and you can feel the edge. Never feel the edge of the part while the spindle is spinning. It will cut you very badly if it's sharp at all.